Right now, okay. So let's start the lecture. So before stating the actual problem which I wanted to talk about today, let me introduce few graph theory terms which I will be using. So if you don't know about, if you don't know anything about graph theory, then also it's fine. I mean, I will introduce every term. So if you feel that you are not able to understand anything, you can just unmute yourself and ask me. Okay, so yeah, so let's start with the first term. So what is a graph? So graph is a pair of, so graph is a collection of some vertices and some edges. So this V denotes my set of vertices and E denotes my edges. Such that, so what my edges do, edges connect two of the vertices. For example, if I take this, so you can take this as an example. So this is a graph where my vertices are
Yeah, I think there's a network issue. Let's give it another minute. Um,
so here you can see that my vertex 1 and okay, so you can see that V1 and V2 are connected. Similarly, my vertex 2 and vertex 3 are connected. Vertex 3 and vertex 4 are connected. Vertex 2 and vertex 4 is connected, and vertex V1 is, and vertex V5 is connected. So basically what my graph is a collection of some vertices and some of the edges which are joining. So each of the edges are joining two of the vertices. And what we see here is a pictorial representation of graph. So if I look at this graph. So wait a minute. So P6, V1, so if you look at both of this graph, let's say this is my graph G and this is graph H. So can you observe that both of the graph uh, actually represent, I mean, structurally, both of the graphs are same. Yeah, I want people to interact, like you can unmute you and say what your observation
Yes.
is.
yeah.
So why they are same? Because see, because if I draw this H graph again, like this V1, V5, V3, and V2, V4, and V6. So see, my H, this is the same graph. These two graphs are same. And you can see both of the graphs are actually structurally same. So, for the two, like the for this graph reconstruction problem, I will consider both of this graph to be same, even though the label on this both of the graph is same. And if we define this, if we look at the name of the vertices, even though they are different, I will say that they are isomorphic. So this is isomorphic. So what I mean by a isomorphism, let me define what isomorphism is. So isomorphism is a function f from Vg to Vh such that if u comma v are is a h in G, if and only if f u comma f is a edge in H. Okay, so can you find the isomorphism between G and H? So you can see, so where my vertex U1 will go, I want someone to respond.
V1, I guess.
Yeah, so you can take U1 to V1.
You can actually
And
choose any one, right? Any vertex for the first one.
okay, yeah, U1 can go to any of the vertex. So where you want to take my U2?
V3.
We can take it. We can take
V3
it
or
to
V5.
V3. Okay, and once my V1 and U2 are defined, I am forced to map U3 to V5. And similarly, U1, U2, U3, U4 will map to V2, and U5 will map to V4, and F of U6 will map to V2, V4, V6. So you can see that this is not the unique isomorphism in this graph. There are many other isomorphism, but right now I'm interested in just defining this isomorphism. I'm not interested in the number of isomorphism which this two graph has, different isomorphism. So what I want you to when I am using this term graph, so I will be using this label V1, V2, Vn for this vertices, so that uh, we are like we are so that I mean because we are interested in the structure of the graph for this problem. Okay, so I am talking about the problem but not actually stating the problem. So okay, so let me define what a order in a graph is. So order in a graph, this is the number of vertices. So order of a graph, sorry. This is the number of vertices in G. And what is the size? That is the number of edges in G. Okay. So till now, I think everyone is fine with me, right? I mean, everyone is. I don't think the position of all the.
Does like above you wrote curly braces UV in edges of G, so that represents an edge, right? The curly braces UV.
I think there may be another network issue. Yes, can you hear? Can you say
Yeah,
something?
I can hear
Ah,
you.
okay. Okay.
Okay, fine. Yeah, sorry for that. Sorry for the interruption. Okay, so
Yeah, Arham
fine.
had a question. You want to say it again?
Does
Yeah.
curly braces UV represent the edge from U to V?
So sorry, can you repeat your question?
You wrote F, V, G, and then in the second line it's written curly braces U, comma V, element of E, G.
G, yes.
So the curly braces thing represents an edge. That's what I'm asking.
Yeah. Okay, yeah. So I should define an edge properly. Okay, so what my edge is? So edge is actually this set. So you will have some collection of UV. Uh, so is sorry. So E is a subset of this particular. U comma V belongs to VG, but U is not equal to V. So for now, we are not interested in any loops.
Okay.
Okay, yeah. So is it fine for you?
Yeah.
Yeah, okay. Yeah, so please don't use the chat. You can just unmute yourself and ask because most probably I won't be looking at the chat. I mean, and if someone put any question in the chat, Sai, can you please tell me about that?
Yes, I will do so.
Yeah, okay. So for example, if we look at this graph G, then the order of this graph, order of G is 6 because there are 6 vertices and size is also 6. Size of G is equal to 6. Okay, so let's now define my subgraph. So let's say I will say that H is a subgraph of G if the vertex set of H is a subset of vertex set of G, and this my H set of H is also a subset of H set of G. For example, if I take my this graph V1, V2, V3, V4, V5. So this is my graph G and this is H. So you can see that H is a subgraph of G. And let me define a induced subgraph. So what my induced subgraph is, again that H will be a subgraph of G. My vertex set H will also be a subset of VG, but
Is it the case that the number of edges and vertices in subgraph should be less than or equal to that one, the one in the G to be, is it a necessary condition for that?
oh, so okay, no, it is not necessary that first of all, the number of edges should be by the way, G and H can be equal as well. In that case, also we say that H is a subgraph of G. But if H is not equal to G, then the number of edges should be less than G. That is the necessary condition. That would be like because that should if my H and G are equal, then only my number of edges will be same. But the vertex set can be same, like VH can be, so if I take this graph, then this is also a subgraph of my G. Hello.
Yes, yes, okay. Got it.
Yeah. Okay. Fine. So let me define what an induced subgraph is. So my vertex set is a subset of this vertex set of H is a subset of vertex set of G, and UV. So if UV is a vertex in H, then U comma V is belongs to this H set of H, if and only if this U comma V is a edge in G. So what do I mean by that is, so how, so for example, this graph H which I have drawn here is not actually an induced subgraph of G, but let's say this graph B2, B5, B3. So this is an induced, why this is an induced subgraph of G, because see, if I take any two vertex from H, P1, any two vertex from H, then they are connected in H if and only if they are connected in G, right? But
Can you
if
please
I,
repeat the statement?
Yeah, I got it.
yes, yeah. So what I am saying is that if you take any two vertices in H, then they are connected in this H. So there is a edge between that two vertices. If and only if there is a edge between that two vertex and G. So if you look at this particular H, then H is a subgraph of G, and H is actually induced subgraph. But instead, if I take this graph, B1, B2, B5, and B3, then H is a subgraph of G, but it is not an induced subgraph. Why? Because see, if you look at vertex 2 and vertex 3 in V2 and V3 in H, then they are not connected in H, but they are connected in G. I'm talking about this G. Is it clear, Prithvish?
Yes, yes.
Yeah. Okay. So,
Wait,
I
so
have started.
would this be correct? If you take a graph and then take any
Uh,
vertex and delete all the edges coming out of that vertex, you get an induced subgraph.
yeah, exactly. So if I take, suppose, for how I get an induced subgraph is, I will delete all the vertices. So suppose my VG is V1, V2, Vn, uh, and my vertex set of H is V1, V2, Vi. Since the labeling is in our hand, I can do that. So what I am doing is from graph G, I am deleting the vertex Vn and all the edges which are starting from Vn.
Okay.
And similarly, I am doing doing this for Vn minus 1. I am just removing the vertex Vn minus 1 and removing all the edges coming out from it. And I will do it till Vi plus 1 and I will get a graph. That would be my induced subgraph. On set V1 to Vi. Fine. Okay, so everyone understood what an induced subgraph is?
Yes, it's clear.
Yeah.
Yeah. Okay. So let's come back to the problem. The problem which I wanted to discuss, this graph reconstruction problem. I started with the definition very like without giving any motivation, like why are we looking at this particular definition? Why we need isomorphism and all this stuff. So let's play a game with graph. So what I do is, suppose I have a graph. Let's say I have this graph cycle on 4 vertices. So a cycle on 4 vertices is like a polygon. Uh, so this is a C4. Usually we denote a Cn to be a cycle on n vertices is something like your vertex set will be V1, V2, Vn, and my V1 will be connected to, so my H set will be Vi, Vi plus 1, from I2 minus 1, and there will be one more edge, which is Vn and V1. Vn and V1. So how the diagram will look? So my cycle on n vertices is like V1, V2, V3, and there will be edges connecting V1 to, and there will be some more edges here. So this is a cycle on n vertices. So what my problem here is, suppose if I
Shouldn't
give
the
you,
cycle be closed? Is there any
yeah,
constraint that it should be closed?
yeah, it should be closed. I mean, something like this, but because I can't draw arbitrary many vertices, so I am just using this dot. It should be a close, it would be polygon-like thing,
All right, all right.
but yeah.
So
So, okay.
shouldn't this closed condition should be defined in the uh, definition that you have written?
It is
Yeah,
there.
so if you look at this particular edge set, the edge set which I have defined for cycle, so it is so you can go from V1 to V2 and V2 to V3, V3 to V4, and dot dot dot. You can go to Vn minus 1 to Vn and Vn to V1. So from there we can say that the graph is closed. Fine. So the problem which I wanted to tell you is, suppose I have a, so let us look at this graph C4. Now what I am doing is, we have 4 vertex V1, V2, V3, and V4. So what I will do, I will delete the vertex V2 to get a graph, this induced subgraph V1, V3. Similarly, I will delete the vertex V3 to get this graph V1, V2, V4. I will delete V4 to get V1, V3, and this one, V3, V4. And now what I am doing is I am also removing the label from the graph. So I will get something like this. And I draw all this 4 graph on a card, and I give you this 4 card. And if I ask you to construct the original graph, suppose I have this C4 graph but I don't tell you, but I am not telling you what the original graph. So I'm not telling you that the original graph which I have is C4, but instead I'm just giving you this card D1, D2, D3, and D4. So right now you know that the original graph was C4, but if I, for arbitrary graph, I give you all the induced subgraph on n minus 1 vertices, and I ask you to construct the original graph using them. So did you get the question what I am asking? So what I am doing is, instead of giving the original graph, I am just giving you the card D1, D2, D3, and D4, and I'm asking you to construct the original graph. So so my question is, can you construct every graph just by looking at the card which I have given to you?
Makes sense. Are there some more restrictions on the cards, or uh, is it just like
Uh,
induced subgraphs?
yeah, so I'm just giving you the, so for example, like in this case, I will not make the life easier for you. I will just give you this thing. So as I will just give you this four graph.
Do we know the induced subgraphs have n minus 1 vertices?
Yeah, I will just delete one of the vertex from the original graph.
Okay.
Let's say V1 to Vn are my vertices in the original graph. First, I will delete the vertex V1. Then I will make the graph, and I will just remove all the label. I will draw that graph on a card. Then I will take the original graph back. I will remove some other vertex. I will remove the label. I will draw that on the second card. And similarly, I will make n card for you, and I will just give you the n cards instead of. I won't tell you what the original graph is, and I will ask you to find the original graph.
Okay.
So the question is, uh, if I gave you the card instead of the graph, and I ask you to find the original graph, can you do that?
This one which you just wrote down is the same as the first one, right?
Yeah, this is same as the first. So yeah, because this one D1 is,
They are isomorphic.
yeah, they are isomorphic, right? So just because I want to, if you look at this in first diagram, this D1, D2, D3, D4, you would be able to guess that this is a C4 graph. But I just want to make your life difficult. I mean, I will just give you some random isomorphic graph to each of the vertex related graph, and I will just ask you to find the original graph. So so the question was, can you reconstruct the original graph? So the answer would be no if I can find any two non-isomorphic graph which have the same deck of cards, which have the same set of cards, right?
Right.
Yeah. So can you find any such graph? Uh, so you can just give me an idea of what you are thinking. But the answer is very simple. If you just think some trivial cases, then you might find a counter example.
So by just looking at the things, the cards you've given us, we can
Yeah,
deduce that the graph has four vertices for sure.
yeah, we can deduce the number of vertices. Sure. Even the number of card will also tell you how many vertices in the original graph. Vertices are there in the original graph. Okay, so let me give you a, hint. I mean, not hint, that is the solution only. So you just look at the graph on two vertices. What are the graphs on two vertices?
All right, it's just two vertices and an edge, and both will have the same thing.
Did you guys understand? Yeah, so did you guys understand the problem which I stated, this
Yeah.
graph? Okay, so have you found any counter example?
Yeah, it
What
can
you
be a
get?
line.
Yeah, fine. So if we take the two graph on two vertices, this G and this H, then the card corresponding to them will be this just a single vertex. And so we can't find the original graph if I give you these two particular cards. Fine. But can you find another counter example with more than two vertices? So were you able to find? Or so okay, so wait.
For a cycle, we can also the cards can also form a line.
Okay, so if you look at a cycle, let's say cycle on how many vertices?
Any and
Let's say cycle on five vertices. If I'm taking a cycle on five vertices, then the four card will be so 1, 2, 3, 4. No. So, so this will be the four card. I will have five. Okay, and what other graph has this same set of card?
a line with 5 vertices.
Uh, so line with five vertices. Okay,
That's not true, right?
yeah, that's not true
Because if you take out a vertex
suppose
from the middle, then there'll
then I
be
will
disconnected paths.
yeah.
In fact, I think for all cycles, we could reconstruct the graph uniquely.
Yes, for all cycle we can actually reconstruct the graph.
Yes, I was thinking that first of all, you can find the number of edges in the original graph.
Okay, so how you will find the number of edges?
Because for every edge which is there in the original graph, it would be there in n-2 of the induced subgraphs.
Right?
So then you just add up the number of edges on all of the subgraphs and then divide by n-2.
Yeah, exactly. So we can actually find this number of edges.
And then
So
you can also find the degrees of all the vertices.
right, we can also find the degree of the vertex. So everyone got the idea of how we are finding the number of edges. So what she is suggesting is just we look at each of the cards we find how many vertices are there. And we will just suppose suppose there is D1 even edges in first, yeah, even edges in first graph, E2 edges in second graph, E3 edges in third graph, and En vertices in n graph, then that would be 2 times the n minus 2. Why this n minus, oh, sorry, not 2n minus 2, that would be number of edges times n minus 2. So see, so if I look at a graph, let's say this graph G, in fact, if I look at, see, if we pick any edge, P1, V2, let's say I am considering this edge, then this will be there in every card except 2. So the graph which I will get by deleting V1, that graph won't contain this edge. And if I look at the graph which I got by deleting V2, that graph also won't contain this edge V1, V2. So all the remaining 3 graphs, particular edge, right? So if we just take the sum over all the edges, so then I will get n minus 2 times the number of edges. So everyone is fine with that we can find the number of edges of the graph.
Yeah, I got the number of edges, but not the degree.
Yeah, okay. So how we can find the degree of all the vertex? So suppose I found the number of edges. Fine. So I will pick a card. Let's say my cards are D1, D2, Dn. So I'm getting D1 by deleting vertex V1, D2 by vertex deleting vertex D2, and Dn by deleting vertex Vn. Take E minus the number of edges in Di. That would be the degree of vertex Vi. So now you understood how we are getting degree of all the vertices. Hello.
Yes.
Okay. So do you know what a degree sequence of a graph is?
No, can you define it?
Okay, so degree sequence of a graph. So degree sequence of a graph is, this is just the list of degrees of all the vertices. So for example, if I look at this graph, then my vertex 1 has degree 3, vertex 2 has degree 2, vertex 3 has degree 2, vertex 4 has degree 2, and vertex 5 has degree 1. So for this graph G, this is the degree sequence. So usually we write degree sequence in decreasing order. So suppose if I just change the label of this graph, I just switch V1 and V1 and V5, then also the degree sequence is the same. Yeah, because I'm not very interested in the label. Fine. Okay, so we have find the degree sequence, we have find the number of edges, but can you conclude from that that if I give you two distinct, if I give you card of two different, all the cards of two different graph, you will be able to reconstruct the original graph. So
Sorry.
hello, yeah. So
Hello,
what I
yes.
was, yeah. So what I was asking is, so we have find the degree sequence using this card. We have find the number of edges using this card. So is this enough for the problem?
No, I don't think so because we can have two different ones, two different graphs which have six vertices and each have degree tree.
Degree 3.
Yes, one is we have two tree cycles.
2, 3 cycles. Right.
Then we attach one vertex of one and to one vertex of other by a pairing.
Like this.
Yes. Then we could
And
also have K tree comma tree.
K3, 3. Okay. Yeah. Yeah. So you can see that this graph G and H are not isomorphic. Why they are not isomorphic? Because see, G has a cycle of this length 3, right? But H doesn't have any cycle of length 3. So they are not isomorphic, but still the degree sequence of uh, both the graph is 2, 2, 2, 2, 2. This is the degree sequence of G and H. So even though we know the degree sequence of the original graph, we won't be able to construct the original graph. So this question was first raised in 1960 by Kelly and Ulam, who said that if two graphs has same set of cards, so same set of cards means all the same set of I mean all the n minus. So what I mean by same set of cards, that there is a isom. So if we look at the n, all the n minus 1 induced subgraph of G, let's say dn is the card, all the n minus 1 induced subgraph of G, and d1 dash, d2 dash, d3 dash, and dn dash are the n minus 1 induced subgraph of H. And if this set of card is same, that is d1, d2, this collection d1, d2, d3, comma, dot, dn is same as, I mean, they are in some different order. I mean, if you can find if d1 is isomorphic to d1 dash, d2 is isomorphic to d2 dash, and dn is isomorphic to dn dash. So what he said that if they have same set of cards, then they will be isomorphic. And
D1 again, D1, like, how is it defined?
D1, what you're asking?
Definition of D1.
Okay, so what my D1, D1, D2, D3, Dn are, so I will just remove a vertex from my original graph. I will get an induced subgraph on n minus 1 vertices.
Okay.
So there will be n manis n minus 1 different induced subgraph. Different means that so D1 is the card I will get by removing the vertex V1. D2 is the card I will get by removing the vertex D2.
Right.
And so what he said was that if two of the graphs are having the same set of cards for them, then they would be isomorphic. So you have seen that in case of cycle, or it was true, and so this is known as the reconstruction problem, that construction problem, that you want to construct the original graph. We want to construct the original graph using the cards D1, D2, D3, using this D1 to Dn cards. So what Kelly Ulam suggested, that if two graphs are same set of cards, then they will be isomorphic. And the problem is that we still don't know if this statement is true or not. So, but we can find some of the property of the original graph using the cards, but can we construct the original graph using the cards? We still don't know. And this is an open problem till now. So we have seen that we can construct some of the properties of the original graph. So now what I will do is I will relax a condition on the problem, that instead of just giving you, so what I did was I just gave you all the n minus 1 induced subgraph, and I asked you to construct the original graph. But now what I am doing is I am giving you all the induced subgraph. So now can you tell me what the original graph is? So let's call this problem induced subgraph problem.
But why
Induced-
should we? Because all the other induced subgraphs of, say, n minus 2 vertices or and lower, they'll all be parts
Yeah,
of the cards that we are given of n minus 1 induced subgraphs.
exactly.
So there's no new information.
Yeah, so
actually.
exactly. There is no new information which I am giving you. But can you prove that you can actually find all the induced subgraph just by looking at n minus 1 vertices graph?
Okay.
I mean, you can definitely find all the subgraph of the uh, all the induced subgraph of this original graph just by looking at the n minus 1. But there is a chances that the graph you will get So I mean, you just want to get the how many times each of the graphs are repeating in the original graph. That is, you understood what I am saying.
Yes, we have to count how many times each induced subgraph
Actually,
appears.
what you are thinking is correct. That this n minus one, this all the cards n minus one induced subgraph will actually give me all the induced subgraph. And in fact, both of these problems are equivalent. That actually you can construct all the induced subgraph using this original this card thing. Like if I just give you d1 to dn, you can actually find all the induced subgraph. And do you have any idea how we can do that?
Also, I think Bhairav has raised his hand. Do you want to say something, Bhairav?
Yeah.
I just wanted to ask, is the one whether we can construct, or is it not known whether two graphs are have to be isomorphic?
Okay. So yeah, we are interested. Okay. So okay, the question. If I understood you right, you are asking me that what is the what exactly I'm asking, that if I have two graphs G and H with same deck of cards, then yeah, I am asking you to prove G is isomorphic to H, or if I give you a deck of card of a graph, I am asking you to reconstruct the original graph. Definitely, if you solve the second problem, then the first problem is proved. But if I prove the first problem, then second problem is not done. Yeah.
Yes,
Why
but
is it not done is my question. Like, suppose we just take all of the possible graphs of n vertices, and then
Okay.
we lay out all the
Yeah.
cards for them. So if we just search all the cards and find the unique
Uh,
sequence which is ours, then we know which graph
mhm.
it came from. So what's the
Yeah.
problem?
Yeah. Actually, so what I meant by yes, you are correct that actually, no, what I meant was that, see, I want a simple way of just reconstructing a graph using the deck of cards. Yeah, definitely, if I have all the n vertices graph, and if I just look at all the possible decks for each of the graph, then I will, and if for each of the graph the deck is unique, then I can find that particular graph for which the deck is matching with the deck which is given to me, and I will just say that this graph is the this. So this is that particular graph is the solution of this particular problem.
So you want
But
a non-brute force approach.
huh,
You
yeah, I
want
want
the
a
approach
non.
which is not brute force.
Yeah, exactly.
Okay, true. So what is the task that we want to do now?
So the task now is you have to find all the n minus 2 induced subgraph. Uh, all the n minus 3 induced subgraph, and similarly, I want to find every induced subgraph. Just by looking at and what I meant by this is that, suppose if the original graph has vertex v2, v1, v2, vn, then I want, then this collection, your collection should have only one graph with vertex uh, vi1, vi2, vir. So what I want is that I want you to make the collection of all the induced subgraph of my original graph such that if I pick any of the any vertex set of my original graph, let's say G is my original graph, then there is only one graph in that collection which is corresponding to that. I don't want two different cards or three different cards of this from corresponding to this vertices, this set of vertices. You understood what I am saying?
Yes.
Yeah. So the answer is yes, we can do that. But now the thing is how?
So we could just look at the n-2 induced subgraph in each card. Okay.
Okay.
So
Let's
now,
say
okay.
G is my original graph and D1, D2, Dn are the card. This is the set of all the n-1 induced subgraph of G. So this is the only information I have. Now what you want to do?
So we can find the n-2 induced subgraph in each of D1, D2 till Dn. So we should get how
Uh,
many
how many we will get? That would
n
be
square? N square? No.
no,
N,
that would be -1 into n.
correct.
Right.
So, and we know that a subgraph can, n-2 subgraph will exist in only one of them, I think.
n-2.
Yes.
So, by the way, how many n-2 vertices subgraph are there for G?
N-2 sub, for G it'll be
So if I have an n vertices graph, then how many n-1
NC2, so
vertices?
n-1 into n/2.
NC2. NC2. Yes. Yeah.
Right, so each subgraph supposing
n-1 into n/2. Right. So, right. Now what you want to do?
just 1 minute, I'll just confirm one thing.
Yeah. Yeah, they can also think about the problem, and if they have some idea, they can give.
Think, see, each one will be counted twice.
Okay. And how do you know that each of them are counted twice? I mean, definitely you are going in the right direction.
Because two of them will be deleted, and then we can either choose that one of them or the other, and then it will be an induced subgraph of both of them, but not any others.
What do you mean by that?
So first, let's just say to without the labeling being removed.
Okay.
So
Yeah,
then,
so
yes,
okay.
we won't consider two isomorphic ones to be the same, and then since we are counting the numbers, it will work out. So in that case, each induced subgraph is counted twice, one by deleting one of the missing vertices, and then it's a induced subgraph of that one, and also for the other. I mean, general
Yeah,
for n minus k, I think it will be counted k times. So then we just take out divide by k each number, and then we get the correct.
yeah, okay. Yeah, yeah, you are right. So what Harav is saying is, suppose if I want to find how many graphs, so okay. So let's say what first let G be collection of all the graphs which I will get by deleting one of the vertex from D1 or D2 or dot 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 Dn. So what I mean is that first let's take D1, delete one of the vertex. You will get a graph. Put that graph in G. Then remove other vertex from D1. You will get a graph. You will add that in G. Similarly, you will do for all the vertices in D1, and then you will move to D2. You will take one of the vertices, you will get a graph, you will add in G, and similarly, we will do the process for all of the Dn cards, all of the n cards. So in total we will get n minus 1 into n graphs. And what Bharat suggested was, let's see how many times are we counting this graph. Vi1, Vi2, dot, Vi n minus 2, since there are n minus 2. So there will be two, let's say Vg minus, this is my set, let's say x. So if I look at Vg minus x, then there will be two vertex. Let's say they are u and v. Okay. So when I will get a induced subgraph on vertices vi1, vi2, dot, vin minus 2. When I am either from this graph, when my induced subgraph on n minus 1 vertices is this, or vi2, vi1, vi2, dot, vin minus 2, comma v. So if the induced subgraph corresponding to these two sets will give me the graph, induced subgraph on n minus 2 vertices corresponding to the vertex set x, right? So the collection J, which we created by deleting one of the vertex from DIs, which consisting of n into n minus 1 graph. So what I will do here is I will just make a pair of the isomorphic graph. So I will take a graph, I will find another isomorphic graph to that particular graph, and I will just pair them. So I will get n into n minus 1 by too many pairs. And from each of the pair, I will just take one of the cards from each pair. Take one card, and that will give me all the n minus 2 induced subgraph. So everyone got the idea of how we are getting the n minus 2 induced subgraph? Hello, can you guys hear me?
Yeah.
So did you guys understand how we are getting all the n minus 2 induced subgraph?
Yeah.
Yeah.
Okay, and so so using the similar idea, we can find the induced subgraph on I vertices when I have if I have all the induced subgraph on n minus 1. vertices. I plus 1 vertices. So what is the idea for that? I mean, the idea is same, like, so in that case, the changes will be that instead of taking pairs, instead of making the pairs, we have to find I many cards which are isomorphic to each other. And we will, sorry, not I, we will take n minus I many cards. So we will find n minus card which are isomorphic to each other. We will club them together to get, and from each, so from each of the group, each of this n minus 1 collection, I will just take one of the cards, and by choosing one of the card from each of this collection, I will get all the I vertices induced subgraph. So let's say what I mean is if V1, V2 dot Vi's, if I want to find this particular subgraph, sorry, Vi1, Vi2 dot Vi, J1, J2, and Ji. Then this Vg minus this set T will have vertex U1, U2, dot UN minus 1. So I will get this particular graph if my vertex set of the I plus 1 induced subgraph is J1, Vj2, dot Vji, and some Uk. So I will get n minus 1 copy of each of the induced subgraph. That's why I'm just taking n minus 1 induced subgraph together, and I'm just taking one from them. So is this clear to everyone? Hello.
Yes.
Yeah. Okay. So we have seen that we can reconstruct the cycle graph from the just by looking at the deck. Can you give me some other class of graph which we can construct using the deck?
Complete graphs.
Okay, so complete graph. How we will do that? I think that is trivial because
Yeah.
Number of edges.
each of number of edges is one of the idea, and also each of the deck, each of the card will be also complete.
Right. Yeah.
Yeah, because if I have a non-complete graph, then there will be at least one card which won't be complete. Right. So, and can you give me some other example? Some other class of graph for which we can construct the original graph using the cards? Okay, so let me give me the next proposition, which will be the generalization of both these things, that complete graph and cycle. So the outcome of this particular proposition would be that both complete graph and this cycle can be reconstructible. Do you guys know what a regular graph is?
No.
The degree.
Yeah, so regular graphs, the graphs in which degree of each of the vertices is same. So if you look at a complete graph, then the degree of each of the vertices is n minus 1. And if we look at a cycle, then degree of each of the vertex is 2. So both of them are example of a regular graph. So what my next proposition says that we can actually construct, we can
So for this, we
construct,
take any one of the subgraphs and look at the degrees of, like within the subgraph, we can look at the degree, and then some of them will have one less degree than they should have. So
yeah, correct. We can construct. So what you suggested was that since we can find the degree sequence by just looking at the graph, uh, we can know it is regular, if the graph is regular or not, right? So now what we will do is we will just pick one of the card. Since since my graph is regular, so the degree will be r. Let's say the degree of each of the vertices are. Now from this card, pick all the vertex v1, v2, vr, which has degree r minus 1. So what I mean by that is you will just find all the vertices which has degree r minus 1 in this particular card. You will add a new vertex to that graph and you will join them with v1, v2, vr. And the graph you will get will be isomorphic to the original graph. So is it fine with everyone?
Yes.
Okay. And see, if I want, so this proposition will imply that complete graph and circles are reconstructible. It also means that this complete bipartite graph, K m comma m, is also reconstructible. Right? Because degree of every vertex is m. In fact, you can actually prove that Kmn is also reconstructible.
I didn't understand the proof for the regular graph. Like, you pick one of
Okay.
the cards, and then what
So,
happens?
okay, so choose all the vertices in this graph. So you are just picking a card. Look at the graph. You will just pick all the vertices which has 1 degree less than the this r. Okay. So
Right.
what does that mean? That since the degree of all these vertices is less than r, it means it was the vertex after deleting that vertex. The graph we are getting.
Right.
Okay. So why we are getting r minus 1 vertices? Because the edge which was connected to this vertices were deleted,
Oh, right.
right?
Yeah.
So that is why we are adding one more vertices which was deleted, and then we are connecting that to all the vertices on r minus 1 of degree r minus 1. So that now the graph has degree, so now the graph is regular, and that would be the original graph.
Okay. Thanks.
Fine. Okay. So you can see that Km comma m is also reconstructible. This is complete bipartite graph with bipartition of size m and m. By the way, you know what a complete bipartite graph is. So bipartite graph is you can. Is there anyone who don't know what a complete bipartite graph is?
I don't.
Okay, so do you know what a bipartite graph is?
Is it that you can
yes,
split it into two parts such that one vertex from one part does not have a edge to another vertex to another part?
Yes. What a bipartite? Yeah, we can partition the vertex set into two sets, V1 and V2, such that each of the edges connecting a vertex in V1 to a vertex in V2.
Oh, okay.
Okay. And what do we mean by complete bipartite graph is that each of the vertex in V1 will be connected to every vertex in V2. So for example, if you look at this graph, this is a complete bipartite graph because each of the vertex in this side is connected to every vertex in this side.
Okay, got it.
Yeah. So you can actually try that we can construct n comma n by looking at the graph. Okay, just fine. Is reconstructible. So you can try. Okay, so does anyone have any idea how we can do that?
How will we know it's a complete bipartite graph to begin with?
Okay. Yeah. Does anyone have any opinion about for that? See, if I have vertex V1, V2, Vn and V1, U2, Um, I'm not taking small vertices cases. Okay. And suppose V1 was not connected to U1. Okay, so they were not connected. Then, yeah, okay, we can't. So we are taking a graph on three vertices at least. We are not considering.
Okay.
So at least fine. So suppose V1 and U1 was not connected to each other. Then if I had deleted V2, and if there was more vertices in this V, then I could have seen that this Vn was connected to U2, Vn minus 1 was connected to U2, V1 is connected to U2, but V1 was not connected to U1. This vertices will be connected to U1. So I can see that this vertex V1 is not connected to my vertex U1.
Right.
But if it was a complete bipartite graph, they should be connected. By the way, the first problem for you should be to actually see if the graph is bipartite or not. I mean to find if I just by looking at the card. Then only you can say that this is not a complete bipartite graph, right? And how you will do that? That you can do by using this proposition that a graph is bipartite if and only if it has only one cycle. So now you can use this proposition and the idea which I told you to actually prove that KMN is also reconstructible. So you can try that. Now the next thing I wanted to tell you is, do you know disconnected graph? So let's look at this particular graph. See, if I want to move from this vertex V1 to, let's say, V3, then I can't go just by, if I can only move through edges and I want to go from V1 to V3, then I can't go, right? So this is a disconnected graph because it's V1, V6, V5, and V2, and this is V3, V4. So what a component in a graph? This is the maximal connected subgraph in this disconnected graph. For example, this is one component, this is two component. So a connected graph has only one component, but a disconnected graph has more than one component. So did everyone understand what a disconnected graph is?
Yeah.
Okay.
Also, I guess Bhairav has raised his hand again. Bhairav, you have something more to say?
Yeah, you
Uh,
can say.
just wondering about an earlier point. I didn't quite get how we can be sure that the graphs in that the points in the card correspond to the points in the graph without any permutations when proving that a regular graph is reconstructible.
When proving the regular graph is reconstructible, what you are asking? Hmm.
How do we know that the how do we know which ones is connected? Do we know the degree, but those are in the card. So how can we be sure?
Okay. Yeah, how can we be sure that that would be connected to R minus 1? That you are asking, or?
Yes.
Okay, so you understood what a regular graph is, right? That
Yes.
degree of each of the vertices is R. Now,
Yes.
if I'm looking at a card, and if I am finding finding a vertex which has degree R minus 1, see, I can find the degree sequence of graph using this deck of cards.
Yes.
Okay, so so I would be able to know the degree sequence of my graph is R comma R comma dot 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 R. So
Yes.
if this card has a vertices of degree R minus 1, what does that mean? That when I deleted that vertices to get that particular graph, the edge which was connecting this that deleted the edges
Oh, yes.
which
Now I see. Yes, we
yeah.
only use one card and then attaching more edges. I thought in some way we were going to use more. Okay, thank you.
No, we are just looking at one card and finding all the vertices of degree R minus 1, and then we are just adding a new vertex and connecting that to all the vertices of degree R minus 1.
Okay, thank you.
So that is fine now.
Yes.
Okay. Yeah. So now I want to see if this. What I want to prove now is that disconnected graph is also reconstructible. And this is little bit non-trivial statement. And what is the importance of this particular proposition is that most of the graph which because if we are able to prove that disconnected graphs are reconstructible, we have actually proved that most of the graph on n vertices are reconstructible because means a large class of graph on n vertices are reconstructible, right? But still the problems open for a connected graph. Like if we, what can we say about connected graph, whether they are reconstructible or not? So this is the last thing which I want to tell you before ending. And the proof is little bit long and it is more engaging. So I think everyone is comfortable with the terms component and disconnected graphs, right? So
Yes.
Yeah.
okay. So I will be using this term frequently. That's why I wanted you to be comfortable with these terms. Okay. So suppose my graph, this, let's say disconnected. So suppose my graph was G, was my graph. G was the graph. And the deck of this particular graph G is given, and I want to compute I want to just reconstruct this graph G using this deck. Suppose G has L component. And there will be one component. So among all the components, let K be the maximum number of, so let K be the number of vertices in component with maximum number of edges. Fine. So my first task is to find if to know if I can find the value of this K just by looking at the deck. So do you guys think that we can find the value of K just by looking at the deck? You can use some result. You can use the result which we have proved earlier. So first of all, you understood what K is, right?
Yes.
So we can just like look through the deck and then we know that the component must be in the K minus 1, must have K minus 1 vertices or less. So it must be in the deck, represented in the deck in some form. And then we can just search and find it.
What you no, I didn't get what you said.
We know that there are at least 2 disconnected components. So
Right.
the component with the max number of edges will have
That's
maximum of n minus 1 vertices.
so suppose my component are H1, H2, and HL. So these are my components. Then,
Yes.
okay, then what you want to do?
So then we can look through the deck and then we can find which the components must be represented fully in one of the cards.
Yeah, okay. So suppose if HL was having K many vertices,
Correct.
and so this is the component with maximum. Sorry. This is not maximum number of edges. This is maximum number vertices. Really sorry for that. Yeah. So
Okay.
suppose, yeah, sorry. Yeah. Do you want to think again or?
Okay, I'll just think once more. I'm not maybe I'll just
Yeah. Okay.
So each component must appear in one of the cards.
Each component must appear in one of the card, right?
Completely.
Yes. So
But what if one component is only one, like,
What?
only one
yes,
vertex?
if there is one component with only one vertex, right, that is also possible.
Or maybe all of the components are only one vertex. So then
Then you
we
can
can say that, right?
just look at the degree sequence and find the, because degree of each of the vertex would be 0,
Oh,
right?
then it's a regular graph again. Okay, I got it.
Yeah. So suppose this HL has k vertices, then and k is the maximum, k is the number of vertex in like the component with max number of vertices, right? So there will be a card which will contain a component with k many vertices. Can you see that why?
Yes, because k must be less than n,
Yeah,
less than
that
equal to n minus
case,
1.
yeah, k is less than n minus 1. But what I am suggesting is there would be at least one card in which there would be a component of size k.
Yes.
Yes,
Yeah,
that's
because you can
Because
just take maybe another component, remove an edge, a vertex from it, and then the
mm,
maximum component still has k.
right. And so what we can do is we can just look at each of the card. Just look at each of the card. Let's define ki to be the max, the number of vertices in component with max number of vertices in that particular, in my card di, right? You understood what ki is? So now what we are doing is we are just looking at each of the card. I am finding this. So the way we defined k for my original graph, I am defining ki for the card, for the graph di. So what I know that this ki would be uh, at most k, right? And at least one of the ki will be equal to k. Fine. So we will just take maximum amount of ki. That would be my k.
in
Did
fact,
you get
sorry.
huh?
In fact, don't we also know this component? Like we can just draw this component by itself. Since
Yeah.
we
So, but yes,
since the
but
okay,
okay,
I'll
okay, yeah. You can say yeah.
so since the component is represented in at least one of the cards, it's represented
Yes.
fully, so we know all the edges within it. So we can just draw the component directly in ours.
Okay. Right. But what if there are more than one component of size k? Suppose all of the component are of size k. Then in that case, what you will do?
And then we can find how many times each component is represented, and then we could probably figure out how many different such components with k vertices are there.
Yeah. So different means non-iso. I mean, okay. Yeah. The essentially the idea is same. Like we will in somehow we will be counting how many times the number of component of size k is coming, and we can use that. But there is one more simple way in which you can actually find the number of components in k cards. So earlier what we proved that using this set of cards, we can actually find all the induced subgraph, right?
Or we can find the k induced subgraphs then
Exactly. We will look
and
at all
see.
the
Correct. Sorry.
k vertices induced subgraph, and we will look at only we will pick only those cards in which that k vertices induced subgraphs are connected. that will give me all the k vertices induced subgraph in the original graph.
Correct.
Right. So everyone got the idea how we are getting all the k vertices component of the original graph?
Yeah, I got that idea, but what is Ki again? Sorry.
Oh, what is ki? Okay, so let's look at. So we had some decks D1, D2,
Right.
dot Dn. So what we define K? So we look at the graph G, we look at every component, and we find that particular component which had the maximum number of vertices.
Yeah.
Now we are doing that same thing for Di. We are just looking at all the components of Di, and we are just picking the one which has the maximum number of vertices,
Okay.
and that is my Ki.
Okay.
Yeah. Now, since you know this K, and now we are also able to find all the K vertices component of the original graph. Now, how we can find the remaining components? So does anyone have any idea? Like, or are you guys thinking about that? Hello.
What if we
Yeah.
take the original induced subgraph cards with n-1 elements, and
With
we find the card in which a vertex is removed only from a component with k. So then if it's removed from a component with k, then all the other components will still be intact.
right.
So
Okay, and yeah,
once we
yes.
find such a card which has only removed a vertex from k, then we can find everything.
Yeah, actually we can find all the component of size 1, 2, or k minus 2. But there is a problem with k minus 1. See, when you are removing a vertex from this k component, k vertices component, then you are getting a k minus 1 vertices. Right. Then you don't know which of the k minus 1 vertices component you should choose to get my which will be there in the original graph.
Yeah.
Yeah, so this is actually a crucial part that we will use that the step which you the idea which you gave to find the component of size 1, 2 up to k minus 2. So till now what we did, we find all the component of size 1, 2, k minus 2 and k, but we are still remaining with k minus 1, right?
Okay, then what now you can do is pick pick an induced subgraph or a card which has, like, we know the number of components, which is I. So pick a card with I-1 components,
I minus 1 components.
if that's
Uh,
possible. Is that possible?
Pick a graph with I minus 1 component means.
Um, in the cards, if we have like we remove one vertex from a component and maybe that component just disappears then. So then we're left with I-1 components.
Yeah, but that means that the vertex which you are removing is a isolated, means a vertex of degree 0.
Yeah, That's
Right.
the answer.
But what if there is no vertex of degree 0?
Yeah, that's also possible. I'm not sure.
Okay, so uh, so we can actually find all the k minus 1 induced subgraph of G, right? All we can find all the
Correct. So
k minus 1 induced subgraph.
and then we know all the k components, like components with vertex k vertices. So we know
Yeah,
the k minus 1 induced subgraphs from those
exactly.
k. So now we can
Yeah,
just compare it and see which ones are different. And even if they are
yes,
same, we can just like take it because we know they could be just duplicated in the original graph.
right. So that is the idea. So we will look at all the k minus 1 induced subgraph which are connected. So this is a which are we will just look at the connected vertice connected like k minus 1 induced subgraph.
Oh yes, yeah, correct.
Right. Let this be all this card is collected in G1, and let G2 be set of how I'm getting G2 is I'm just looking at all the k vertices component. I am deleting one of the vertices from them and putting that in G2. So suppose there are L components of um, size k. So you understood how I'm constructing G2. I'm just taking a k vertices. Uh, so I'm just taking a k vertices component because I know what all k vertices component I have in the original graph. I'm just taking one of the k vertices component. I am removing one vertex. I will get a k minus 1 vertices. I will put that in G2. Again, I will take the k vertex component. I will remove the other vertex. I will put that in G2. Similarly, I will do that for every component of size k. And what I will do is, so there is a chances that when I am removing a vertex, I will get a disconnected graph. So I will just leave that particular card. I won't keep that in G2. I will just take the connected k minus 1 vertices graph obtained by deleting a vertex component of size k. So now what I will do is from this set of cards G1, I will remove all the cards which are also there in G2. So I will just take G1 minus G2, and that will give me all the k minus 1 vertex component. So did you understand how we are getting this? Why this G1 minus G2 is k minus all contains all the k minus 1 vertex component of the original graph? See what that G1, what was the problem with G1? This set G1 has one problem. that there could be some graph in G1 which are actually which we get by this k vertices component, but we don't want that particular set of graphs in our k minus 1 induced subgraph. That is why we are removing G2.
Yes, got it.
Yeah, so did everyone got why I was removing G2 from G1? Yeah. Hello, is everyone there? Or
Yes,
Yes.
okay, so did everyone follow what the last step was?
Yeah.
Yeah, okay. Yeah, okay. So if everyone understood that, so this was the thing I wanted to discuss today, this graph reconstruction problem. Uh, Sorry because there was some internet issue in between. Also, there are some other problems which are related to the graph reconstruction problem, uh, which are also difficult because this is also, I mean, this is also we don't know the solution of, and there are some even harder problems. So suppose instead of just looking at the n minus 1 vertices component, what if I gave you n minus 2 component vertices in n minus 2 induced subgraph or the n minus 2 induced subgraph? Then could then what was then what would have been your answer?
I mean, we would probably try to form n minus 1 induced subgraphs from those. We'll have to think.
Yeah, see, if you were able to prove this n minus 1 vertices, n minus 1 induced subgraph problem, then you would be able to prove n minus 1 induced subgraph problem. But the thing is, there are more. But there would be some non-isomorphic graph in less smaller number of vertices, which would be uh, even though they would be non-isomorphic, their set of n minus l induced subgraph will be same. For example, if we just take vertices on L plus all the graph on n plus 1 vertices, then all the n minus l induced subgraph will have only will be just one vertex. So all the n minus 1 induced subgraph of all the l plus 1 vertices graph would be same. That would be just a singleton vertices, right? So now the problem is which all graphs are actually reconstructible using just if I just give you the n minus l induced subgraph. That could be a problem which could be a generalization of my original problem, right? And there is one more different problem which is natural to ask is what if instead of deleting the vertex, I deleted the edge? That is known as the edge reconstructible problem.
So do these have like, are these open or have any of them been proven till now?
Yeah, they are actually open problem. This n-L induced subgraph problem is also open. I'm not sure about edge reconstruction problem, but so there is one more different direction in which people, which is also interesting, and you can think about that. So the problem is like, what if I lost one of the card from this n-1 induced subgraph? Then can we say what the original graph is? Yeah, so we have seen that some of the graphs are reconstructible using this n-1 induced subgraph. But what if I lost one of the card? Then can we reconstruct the original graph? And there have been some research going on that area, and there is one very interesting result by Bolubas. They say that uh, almost uh, uh, okay. Do you know what asymptotic means? So if we look at asymptotically, all of the graphs, okay, asymptotically, the graph can be constructed using graph can be reconstructed using this three cards. So what I mean by that is, if you let's for define n, this let define R3 to be set of all graph for which there are three n-1 induced subgraph unique to them. And let's A and G be all graph of n vertices. Then what Bolubas conjecture say is that this limit R and G where A and G is 1. So what does that mean? It means that if I take a graph on a very large number of vertices, and if I look at the n-1 induced subgraph of that, so there is a very high chances that if you just there would be three cards, and using that only three cards, you would be able to construct the original graph. You don't need any information regarding the other n-3 cards. So it means that this three card would be like unique to each of the graphs, unique to that particular graph. So this is a very powerful result. Like you are just constructing the original graph using only three cards, right?
Yes.
By the way, I mean, did you understand what that statement of Golubas is?
What's the meaning of asymptotically? That's the only thing I.
So asymptotic means this limit tend to infinity. I mean, so you understood what RNG and ANG is, right?
No, I just missed it, I think.
Okay, so RNG is the set of, so you just look at every graph on n vertices, and and you pick only those graphs for which there is a three induced subgraph which is just unique to them, and you just put that graph in RNG.
Okay.
And now let's ENG to be the set of all graphs on n vertices, all different non-isomorphic graph on n vertices.
Yes.
And if you take the ratio, then you will get something of something which is a function of n. So let's suppose this RNG by ANG is something function of n.
Okay.
And when you take n to infinity, then this ratio will converge to 1. This is what the Bolubas conjecture says.
But but how's it? It's a little too strong, right?
Yeah, this is very strong. I mean, you are saying that for every graph, like if you are taking a graph on very large number of vertices, then among all the vertices, you just need to look for 3 cards, and if you look at that particular 3 cards, you will be able to reconstruct the original graph. That 3 card will just define what my original graph is with a very high probability.
Oh.
And as you increase the value of n, the probability will also increase.
Okay.
Yeah. Yeah, so that is what I wanted to discuss today. Hope you learned something interesting.
Yes, definitely.
Yeah, sorry that there was some internet issue. This does. Yeah.
Thank you, Bhaiya.
Yes.
Yeah.
Thanks a lot for teaching.
Okay, thanks for joining the talk.
Bye bye.
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 Bye.